Good morning, everyone. Welcome to our first press conference of this AGU fall meeting. I'm Peter Weiss. I'm the Public Information Manager. And just quickly wanted to say that we welcome questions after all the speakers have spoken, but only questions from people who are registered as press, who are working press. We do have press officers registered. They're not welcome to ask questions. So please obey that rule for us. Thank you. So we'll get started now. Our first press conference is first results from the Interface Region Imaging Spectrograph, or IRIS mission. And our speakers are in order of speaking. Alan Teitel, IRIS Principal Investigator at Lockheed Martin's Advanced Technology Center in Palo Alto. Bart Depontieu, IRIS Science Lead, also at Lockheed Martin's Advanced Technology Center in Palo Alto. Mats Carlsen, Professor at the Institute of Theoretical Astrophysics at the University of Oslo, Norway. Scott McIntosh, Section Head, Solar Transients and Space Weather at the National Center for Atmospheric Research, High Altitude Observatory in Boulder. And S. Pete Worden, Director of NASA Ames Research Center in Moffett Field, California.
Okay, I'm Alan Teitel. I'm the PI. IRIS is a NASA small explorer that from start to launch took about 44 months to build. And its task is to understand the interface between the solar surface, which is about 6,000 degrees centigrade, and the corona, which ranges over 2-3 million degrees centigrade. And that region has not been explored intensively, and IRIS's task is to do that. So first slide. So the goal is to understand how the energy is transported from the visible surface through the chromosphere to the corona. And this is a very complicated region where lots of things are happening. And the reason we haven't been studying this intensively is because we didn't have the tools to do this. The numerical simulations that are required until about a decade ago were just not feasible. During the IRIS mission, we've spent about 50 million CPU hours generating simulations to compare our data with. So for the first time, there are 3D numerical simulations of how the entire outer atmosphere responds to the surface evolution of the magnetic field. We knew from Hinode and TRACE and SDO that things were fast. So IRIS has 20 times the temporal resolution of any previous experiment and 25 times the spatial resolution. And it forms a bridge between the Hinode observations and those of the Solar Dynamics Observatory. And this is another numerical simulation that was done by Mats and Viggo Hanstein at University of Oslo. This is what TRACE looks like. IRIS looks like, I'm sorry. It's relatively small. It's a little over 2 meters long and about 3 meters wide. And this is what it does. On the left, right, is an AIA image in the 1700 angstrom band. And we can't show an AIA image at full resolution, but we can make a little region of that and expand it. And so the image on the left is the full resolution of AIA. And the pink box is a field of view of IRIS. And you can see that IRIS now, with 6 arcsecond pixels and diffraction limited performance, exceeds what we can see in AIA. This is not a put down of AIA. AIA was designed to look at the full sun, and so it doesn't have we couldn't devote all those pixels to the AI image, would never be able to get all the data down. And so this is a picture that in silicon-4, which is formed at about 1400 degrees Kelvin, 21 hours after opening the door of the experiment. And we see all of this fine scale, which we had not anticipated. And we see it changing very, very rapidly. We had expected that all of these small structures would change very rapidly. We'd seen this previously in Henode, but we were not aware of how prevalent it was and how complicated the connections were inside sunspots. But this is something that in principle could have done a long time ago. This is something that people have tried to do for a long time. This is the first light spectrum of the magnesium H and K regions that were taken, again, within the first 21 hours. And if we enhance that, we can see in the box that's highlighted a region that looks like there are two spectra, and that's because the atmosphere is very complex, and there are layers, essentially, that have different densities and structures. Now, oh, that's too bad. This is something that IRIS can do that is allowing us to get a lot of insight. On the right-hand side, you see the magnesium-2 line, and as the blue line moves through that line, we get another image of the sun. And those images of the sun are from different regions of the atmosphere, different temperatures and densities. And so at the same time, we have both the spectra and the image. So this image is created by taking lots of spectra, scanning across the sun, and then reconstructing the image from the spectra. And this is a numerical simulation of that. So on the right-hand side, you see an image that's made in a numerical simulation. The numerical simulation has all the information in it. And so when we let this move, we see the spectra and the image at the same time. And as a final shot, we can use this to get data. So the line across the sunspot goes through a little bright point. On the left-hand side, you see a spectrum, and you see a large protruderance. And you can see this tiny little bump that's about 200 kilometers, going at 200 kilometers a second. So for the first time, we can not only see the structures, we can actually measure the dynamics. So we can measure the heat flow, we can measure how fast things are changing. So we've made a giant step forward in characterizing the heat transfer properties of this region between the visible surface and the corona, which is key to understanding how the outer atmosphere of the sun exists, and key to understanding the atmosphere the Earth flies in, because we all live in the outer atmosphere of the Earth, of the sun. And I'll turn it over to Bart.
Okay, thank you, Alan. So as Alan was saying, we're looking at the interface between the surface and the very hot corona. And one of the things that we realized, we've long realized, is that a lot of the energy that drives the heating of the outer atmosphere, most of it actually gets transformed or deposited in this interface region. And this interface region plays this critical role in terms of the mass cycle between this cool plasma on the surface and the hot plasma in the outer atmosphere. in the corona and the solar wind. And this movie here kind of illustrates the richness of the iris images. This is what we call a slit jaw image. You see the Earth to scale, and off the limb, you see a variety of processes that we've observed in the past, but we'd never observed them with this kind of spatial resolution and with this kind of great thermal coverage, because iris covers temperatures from about 6,000 Kelvin all the way to 10 million Kelvin. In this case, we're looking at gases that are about 65,000 degrees, and you can see off limb these little jets that shoot out, these fountains of gas that are going at very rapid speeds of hundreds of thousands of miles per hour. We also see plasma that's cooling down and falling down out of this hot atmosphere. We see prominences and all. In this kind of brief time, I'll give a few examples of how the data of iris is kind of puzzling us and befuddling us and at the same time exciting us, because there's a lot of new information in there. And one of the pieces of new information that we have is that we can not only image stuff on the sun in this kind of understudied region, but we can also now split up the light into its components, look at spectra. And the two panels on the left are spectra. So the horizontal axis here is wavelength, and the wavelength can tell us properties about the density of the gas, the temperatures of the gas, and in particular here, the velocities. You see all these little high velocity events, these little brightenings that shoot out from these straight lines that you see, vertical lines that you see. There's a little horizontal lines that live for a very short time, and they indicate very high speeds. They indicate speeds of the order hundreds of kilometers per second. The beauty of iris is that we can trace the plasma as it cools and heats, because that's one of the key characteristics of this region. In the past, we've observed this region. We've never been able to really follow the plasma as it gets propelled upwards, heats, and then cools back down, or continues to heat. And that's what we're now doing with iris for the first time. And we find a lot of violence in the solar atmosphere in this particular region. One example of how complex things become once you start really getting this kind of data is a prominence. And a prominence is the cool stuff that's hanging off the limb here in the panel on the right. You see all of these slowly moving features, or apparently slowly moving features. What iris is doing is, with that black line that's moving vertically, is it's rastering that region, and it's building up spectra, which you see in the two left panels, as it's doing it. And with these spectra, we're just flabbergasted by the enormous complexity of the spectra. We're seeing along the same line of sight 3, 4, 5, 6 different velocity components. If we go and look at very high temporal cadence movies, this is a similar movie where we're looking at 65,000 degree images on the right, and we're seeing the spectra, i.e. the velocities of the gas, at 15,000 degrees. And we're seeing an enormous amount of complexity, as I said, where whenever you see these multiple components that are the stuff that's kind of dancing around in the left panel, essentially involves gases that have a specific velocity, and along your same line of sight you have other gases that have other types of velocities, and you can see in the movies at the same time of the images the enormous amount of turbulent motions that you see there. We've seen these kinds of turbulent motions before with the Japanese Hinode satellite a few years ago, but for the first time now we can trace these plasma blobs as they get heated or as they cool down, as the case may be, and we can measure their actual physical velocities using this Doppler effect, the way these spectral lines shift as the light moves towards us or away from us. And so when we show this kind of data at meetings, our colleagues who are trying to model and understand these features are very puzzled and challenged. Why do we care? These prominences play a critical role in space weather. Understanding the dynamics in these events, they often erupt, is clearly something that's of interest to understanding how the sun impacts Earth. Another example where we've really learned a lot already from the data, and where we also kind of highlight how iris bridges a gap between the surface. You're seeing a movie in the upper left there that was taken with the Hinode spacecraft with a NASA instrument on board the Japanese satellite. The lower left is what AIA, which is the Atmospheric Imaging Assembly on the Solar Dynamics Observatory, shows. And essentially, in the past, we've had data at about 10,000 degrees, and 100,000 degrees. And what we're seeing here are fountains of gas that are being propelled upward. They live for a very short time. They're spicules. We call them spicules. They only live for a very short amount of time. They're very fine-scaled. And previous instruments have either had trouble resolving them spatially or temporally, or actually seeing what happens to them. They've been very puzzling. We think they may play a role in providing plasma from the cooler regions of the sun into the hot atmosphere. What we can now do for the first time is shown on the right side, where we see the thermal evolution. We can diagnose the physical conditions in the plasma now, and we can see how it changes in the course of a few minutes, where it traverses distances of the Earth's diameter. And we can see how it heats from 10,000 to 15,000 to 65,000 degrees, all the way out to 100,000 degrees. And by doing that, we can also measure, this is a similar movie to what Alan showed, we can measure the velocities they reach at the same time. And here on the left, you're seeing a spectral line profile, and by scanning through the spectral line profile, we're not only looking at different heights in the atmosphere, we're also diagnosing different velocities. And so we find we can essentially diagnose that these things are swaying very strongly. By quantifying that, we can constrain things like these numerical models that we've talked about. And these are highly complex. I'm not going to explain all of this stuff, but this blue feature that forms is one of these types of jets, we think. But there's a lot of discrepancies between what we see in these models and what we see in the iris observations. And by using all this rich iris data, we can really improve the models. And Mats Carlson is going to talk about that next.
Yes. Well, first about our simulations. We make a model of a rather small part of the sun because of computational limitations. We can't really do the big regions yet. And we build up in the computer a model where we implement the same physical laws as those obeyed by the sun. And we also calculate how the simulation would look like if it was observed with the IRIS instruments. And this is very compute intensive, and it wasn't really possible until rather recently. And the NASA high-end computing facilities at NASA Ames have been really crucial for this part of the IRIS investigation. But we all have also used almost 10% of the capacity of the Norwegian supercomputing network and computing time offered by the Partnership for Advanced Computing in Europe. And the simulations have been used in several ways. They were used also before IRIS launch, and enabled testing out observing sequences and data reduction procedures by using these synthetic observables. Now we use the models in order to try to make a translation between the observables and the actual physical conditions on the sun. What we observe is really intensity and Doppler shifts, and not directly what we want to determine, temperatures, densities, and velocities, and the models enable such a translation. And for the first time, such detailed models are now released to the community. So from today, the full simulation cubes with all the data are made available through the IRIS website from the European Hinode Science Data Center in Oslo. And now for some illustrations. This is now a movie showing a slit jaw image in the silicon 4 line formed around 65,000 Kelvin. And we see there these jets that Bart was talking about, but we also see some lower lying loops of bright emission. And if we now take this red box is the size of the numerical simulation, and we can make the same observation. We can observe the simulation with the same filter, and this is what the simulation looks like if observed with the silicon 4 filter on board IRIS. And we see the same low-lying loops, and they're very dynamic, and we can now understand how they come about, and we have access in the simulation to all the variables like temperature and density, and we can see how they are created in the simulation. But we also see here a big difference. We don't see all these jets. There are some, but they're not as abundant as in the real sun. So I'll come back to that. So in the simulation, when we look at the temperature now, the red and blue are the magnetic field, and in gray we see a different temperature. This is 100,000 Kelvin, and we step up in temperature, and at 200,000 Kelvin we see a whole different set of loops. So we have two sets, one at lower temperatures below 100,000 Kelvin and another above 200,000. We can also make spectra, and at the top there we have, to the right, we have a slit jaw image, and the dark black line is the iris slit. And to the left we have spectra in two regions. One is with the carbon-2, singly ionized carbon lines, and then the magnesium-2 lines that we've talked about. At the bottom you see simulations. So now we have used the same instrument, same spectral resolution to observe the simulations. And there are several things that are immediately obvious here. One is that the simulation box is really small compared with the field of view of iris. And still, it takes millions of CPU hours to perform such a simulation. So we can do with even more computing power. So we're limited to rather small regions. We can't really do sunspots. We can't do active regions in this amount of detail. The other thing we can see is in the magnesium spectra, sort of the middle bottom there, we see many of the same features as in the observations, but the magnesium lines themselves, they're not as wide as in the observations, and we don't have as much emission as in the observations. And these differences, they tell us a lot about what is missing. We can use the translation, we can see in the simulation how a certain observable depend on the temperature and so on. So we see it here from the comparison that in the simulation we don't have high enough temperatures in the chromosphere. The sun is hotter in the chromosphere and it's more dynamic than in the simulation. And then we need to go and try to figure out what is really missing in the simulation. And then we can, when we have the simulation, we can look at it not only from the Earth or the Iris orbit, but we can also see what it would look like if we flew towards the sun. So this is now how it would look like if we had a satellite and could fly about 10,000 kilometers above the solar surface with eruptions and all sorts of things. Well,
yeah. So, as Alan said, IRIS aims to understand or answer a long-standing question in our field, and indeed in the whole of astrophysics. Why does the sun have a corona? Why do you care about this? Well, we live in the sun's outer atmosphere and its corona. It has a very direct impact on Earth, but as we've also heard, we have very little information about how that corona forms. The corona has been studied in great detail in the past because it's relatively easy, especially if you can get out of the Earth's atmosphere, to measure its gross physical properties. But that hasn't really allowed us to develop a fundamental understanding of that layer, because we don't know much about the processes that are actually forming it, the processes that are responsible for its formation. The things that we're starting to see, that Bart's shown, Alan's shown, and Mats have shown, allow us to start to understand those formation processes. The interface region, this coupling zone between the surface and the outer atmosphere, is clearly where a lot of action's taking place, where the corona and the solar wind derive their power. It's the place where a lot of the vast reservoir of internal magnetoconvective energy, the bubbling of the solar interior, gets converted. That energy gets dumped there, and you get pretty much left with one light bulb per square meter's worth of energy. It's only a few % of the reservoir. So you can think of this transition region as an energy shredder. There's somehow a lot of energy that's in the sun's interior is transported upwards, but doesn't make it all the way out. It gets dumped there. We don't understand why, but we're trying to figure it out. As Bart shown earlier, some of the beautiful examples in the movies running right here of the mass cycle, the heating and cooling of material. By understanding the upflows and downflows, the heating and the cooling, we'll be able to piece together how the atmosphere is structured. All phases of it. Then you've got the solar wind, that erratic flow of charged particles that drive into interplanetary space. That is sourced also in this interface region. But our knowledge of the solar wind is also rather vague. And understanding the solar wind is critical for something called space weather, or the impact of transient events from the sun on the Earth. You can kind of think of our knowledge of space weather like terrestrial meteorology about 50, 60 years ago. We don't really understand it very well. But in order to understand when explosions from the sun arrive at the Earth and with what impact, you have to understand the medium through which they travel. Think of it as trying to understand the weather that a cyclone or a hurricane is going to flow through. It's probably better to be able to predict where that hurricane is going to end up if you know the medium it's going to travel through. And so IRIS is the same way. We're trying to understand the background winds so that when an impulsive event travels away from the sun, we know what it's going to travel through, how fast it's going to travel, and hopefully when it's going to hit the Earth. You know, those are the key reasons why IRIS was built, and it's also the reason why the numerical simulations have been developed, because they're like a glue. They help you understand the nuts and bolts, physical parameters, allow you to match what you see with the real physical quantities so that we have a better idea of piecing things together. Luckily for us, IRIS doesn't operate in a vacuum. Chortle, pardon the pun. It's been supported by a host of ground and space-based observatories. And when you put these pieces of the puzzle together, you start to build a very comprehensive picture of how mass and energy are transported through the atmosphere, the likes of SDO and Hinode. And we've been really lucky that we've got a rich environment of observatories to deal with. Couple that with the simulations, we're at a chance to interpret the observations and understand the powerful mechanisms that drive the sun's outer atmosphere and corona. With that, I'll hand off to Pete.
Well, thank you. As the director of NASA Ames Research Center, I really have two roles. One is I'm a co-investigator on IRIS, so exciting data, although I have to confess I'm behind in doing my part of the work. But I just wanted to make a couple key observations here, really on behalf of NASA. We partnered with the Lockheed Advanced Technology Center to build and operate this system, but it's an example of what we can do with a very low-cost small satellite, and this is a direction that NASA increasingly is interested in going, to do more with these smaller, fast-paced satellites. We get more science, particularly with the budget challenges. So I think one of the first messages that really to take away from IRIS is what an impressive set of scientific results we can do. Second, and this has been touched on here, the whole question of space weather and its impact on the Earth's environment, which is one that has increasing interest to not just the scientific community but the public, as we become more and more interconnected through things like the internet and communication systems. Our vulnerability to space weather is increasingly a concern. As noted here, by understanding where the roots of this weather exist and how that impacts the development of solar hurricanes and so forth, is our first step to really getting the understanding we need to be able to predict and understand the effects on the Earth. So we're very excited about this mission. I'm excited as a scientist who's part of the team, but I'm also excited as a NASA person about what it means for our future. Thank you.
Okay, so we're ready to open the floor to questions from reporters only, and we'll also be monitoring the chat for questions. So does anyone have a question?
Yes, good morning. This is Randy Shostak, reporter with EOS, newspaper of the American Geophysical Union. And I'd just like to follow on one of the last comments that you made just a moment ago about the budget challenges. Could you please elaborate on the budget challenges that you were faced with?
Well, as everybody knows, of course, we were shut down for about 2.5 weeks. You know, we're still looking at potential sequestration problems, and NASA's budget in real dollars is the lowest it's ever been since we were created as an agency. So one of the objectives is how do we get more with less. And we're seeing increasingly missions such as IRIS are increasingly important for what we're doing, and even smaller missions. And how do we get the cost down of these things so we can do more? You know, one of the problems with science is that you know, if it takes 10 or 15 years to develop a mission and iterate on that, that's not the way science is done. You really want to have an idea, fairly short order, do your experiment, and then move on to the next question. IRIS, like any mission, is opening more questions than it's going to close. So we'd like to get on to the next one, and we think that the smaller missions, this was a small Explorer class mission, and even smaller ones have huge potential to help us, you know, get the exciting stuff that's out there with the very limited budget we have.
Oh, hi there. I'm Rebecca Morell from BBC News. Thanks for the presentation. You said that you found that things are changing very rapidly. Do you have any idea how this actually impacts space weather from these early results that you've first been looking at?
No, go ahead.
Stunned silence.
I really don't completely understand the line of your question.
I suppose what I'm asking is, the whole purpose of the mission is to try and, you know, understand what's happening with space weather and be able to predict it. With what you've found so far, have you answered any more questions about space weather and how you can predict it?
Not about space weather. We're in the very early stages of this mission. What we have found is that we are now capturing a lot of phenomena that we suspected had to exist, partly from the simulations, partly from previous observations, and that the goal of making things operate as fast as they can is bearing real fruit. It's sort of the situation that we've been in as if you were studying hummingbirds with a still camera and taking clicks just as fast as you could. You'd never understand how a hummingbird flew. It wasn't until people developed very high-speed cameras that you could see what was really happening and how they could hover and go backwards. That's where we are right now. We're just at the point where we can see where the physics is. And we have this wonderful tool that MOTS has led of actually having simulations. And so when we see an observation, we can begin to interpret it. We can go back to the core physics, to the atomic physics and the heating processes that create it. I hope that's a start.
Are there any questions from the chat? Any other questions from the room? Okay. Well, that ends this press conference. Thank you very much.
Can I make a remark? That
Yes.
all of this data is available on the web, at a website. Not only can you get all of the IRIS data, you can get the coordinated observations with HINODAY and with SDO and with the stereo missions. So at one place, a scientist can get access to all of this data in essentially near real time now.
Okay, well, thank you very much. Thank you for your presentations, and thanks everyone for being here. Also, there's further information at www.nasa.gov/IRIS, all uppercase. And also, I'd like to draw your attention to the AGU virtual press room. So reporters, if you're looking for press releases about presentations at the meeting, please go online to the AGU virtual press room. And press officers who want to upload press releases or other materials are welcome to put those up there. We're also going to put video of the press conferences onto the virtual press room. Our next press conference at 9 is update from Gale Crater, results from the Mars rover Curiosity, and we'll look forward to seeing you back then.